Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and with me is...
Robert Moore.
So, Robert, this is our 19th episode. You believe
19. I can't believe it. It seems like it should be more than that in some ways. And in other ways, it seems like it should be far fewer. I guess it just starts kind of blurring together after a while.
And do you think we're getting any better at this?
I think we're getting considerably better. If you go back and look at those first ones, we definitely have fewer technical glitches and everything going on. So I think we're getting better.
It's been definitely an interesting experience.
It has. And we'll get better still.
Right. So in this podcast, the main theme is to talk about science in general, but in particular, focusing on astronomy, astrophysics, and physics. If you have any questions at all during the podcast, don't hesitate to use the live chat. So you can send us any questions that you may have on anything that we discuss, or maybe something that's on your mind that you'd like to talk about. Now, we are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota, where today, Robert, as you probably heard, we're expected to reach a record high.
Yeah.
99 Fahrenheit, almost triple digit.
That's just incredible. I got to admit, when I moved up here, I thought I'd left all the temperatures like that behind, because it's not just the temperature either. It's humid out there. And holy cow. For those of you who may not realize this, I'm a good old South Louisiana Gulf Coastal person. So, my friends down there, I'm sorry for y'all because y'all are baking even worse.
Well, it was interesting because just a few days ago I was going through some photos and I came across a photograph that was taken in late April of snow on the ground.
Right.
So we've gone from having snow in late April to now reaching nearly triple-digit temperatures. And it's not even summer yet.
It's not even summer, which I think is one of the points you wanted to mention.
Well, summer does start tomorrow.
Yep.
It's June 21st, the summer solstice. Now, to be really technical on this, summer starts at officially 9:57 a.m. Central Daylight Time. Now, Robert, here's a question.
Oh, Lordy.
Why are we so specific in the time? Where does that come from?
I honestly don't know the answer to that. I'm guessing it's because that's when we meet Perihelion. That's when we cross through Perihelion at about that time? Or is it...
When is the Earth closest to the sun? Which month of the year?
That would be December.
January.
January, okay.
That's perihelion.
Okay.
Right? We are furthest from the sun in July.
So that'd be aphelion. That's right.
That is a question I actually asked my intro astronomy students. Because you get this, you're trying to look for a correlation with the orbit of the Earth, and that if you live in the northern hemisphere, it's the warmest in the summer, so let's say the month of July, that people get this idea that if you don't know the orbit of the Earth, that we're somehow closest to the sun in July. And that's actually the opposite. We are the furthest at aphelion in July. We are closest to the sun in the first week in January, when typically it's the coldest for us.
Right.
It's just that the tilt of the Earth's axis dominates the climate, the weather.
At one of the previous universities I was at, I got asked to sit in on and then teach a couple of days for a climate class. And one of the topics I got to cover, obviously they timed this for that reason, was about solar insolation. And that's what it's about. Not insulation, insolation.
Right.
And it's basically how many daylight hours, what the intensity of the sun in your location is. And, when you add that, because the more directly the rays coming in, the more higher the intensity of this solar energy, the more solar energy you're getting. And then on top of that, we're getting, because of the tilt of the Earth, we're getting that increase in solar energy for longer periods of time.
Right. So the thing to look at is the area on the ground.
Mm-hmm.
Let's say 1 meter by 1 meter.
Right.
So 3 feet roughly by 3 feet. How much energy does that patch of ground receive from the sun over some period of time? Let's say 1 minute. When the sun is higher in the sky, like it is in the local summertime, then we're going to get more energy received by that patch, that area on the ground. Then in the wintertime, when the sun is much lower in the sky, And that amount of light that normally would fall on, let's say, that one patch, then is spread over a much larger area.
Right. And I looked up the insolation numbers, and for some place like North Dakota, in January, it's going to be down around 400 or 500 watts per square meter at noon, whereas during the summer, like right now, it's over 1,000.
Right.
So this is why we're having the temperatures we are. This is 1,000 watts per square meter. That means on a box that's roughly, for Americans, 3 feet on a side, you're getting 1,000 watts. It takes about 300 watts to run a dryer, a clothes dryer. So you're talking enough energy hitting a 3 foot square box to run 3 dryers. That's what we're talking about.
Right. And then getting back to why this is it the first of the summer at 9:57 a.m.
Right. I'm curious.
Central Daylight Time. That's from the exact middle, the geocentric center of the sun is at that position, the furthest north of the equator that it's going to be.
Okay.
So just like when we say, for example, the first day of spring is a certain time, that's when the exact middle of the sun then passes, is right on the celestial equator, right on its way north for us in the northern hemisphere.
Okay.
So it's based on where the positioning of the exact center of the sun, where it's located. That's how we can say, okay, summer now officially begins at this time.
Okay.
And because we have a great understanding of where the sun is, you can get that very, within a fraction of a second, you could say, where's the middle of the sun?
Right.
When is the furthest that is north of the celestial equator at that point, right? When it's going to be the furthest at 23.5 degrees, north of the celestial equator. And that would signify the beginning of summer.
Okay. That makes sense. I always wondered how they pinned down that exact time like that, but that makes sense now that you're mentioning it.
Now, if you're an astronomer, of course, and I mean like a traditional optical astronomer that wants to look at things in the night sky, this is a bad time of the year.
This is the worst time of year.
Now, why is that, Robert? Can you explain that?
I can explain that. I get here in North Dakota, if we go out to the telescope, we have precisely 1 hour of true darkness.
Right.
That's right, 1 hour, because you got to take into account all the twilight hours. So the sun may not be above the horizon, but its light is actually being refracted into our atmosphere. And so it's not truly dark except for that 1 hour roughly.
Now, if you had an opportunity, somebody lived in the far north and he said, come visit me, Robert, and during the summer, and don't forget to bring your telescope, would you bother if you're just going to look at stars?
No.
Other than our sun?
No. If I had an H-alpha telescope or calcium K, something like that, I would absolutely do it because, holy crap, up in Alaska, you'd have 10, 12 hours of being able to look at the sun. And if you went far enough north, you could see the sun all day long.
That's what I'm getting at. So the sun is always above the horizon in the far north.
Right.
During the summer months. And then, of course, the opposite, then in the wintertime, then the sun is always below the horizon. So that would give you the advantage that you could actually look at the stars, 24 hours at a time, if you can stand the cold, of course. Right?
And I was about to say, that's part of it's one of the weird quirks about living this far north is during the winter, we only get about 6 hours of daylight.
Yeah.
But during the summer, it'll be 10 o'clock tonight before the sun's really dark. It's starting to get any kind of dark.
That's right.
So it's kind of, and the sun's up before 6 o'clock. I know. And hello to you too as well, Mizuho.
But so anyways, what a lot of things that we tried to do on this podcast is pick some interesting topics, things that are happening, current events type of situations and so on. And one of the things I was thinking about doing for this podcast today would be to look at maybe our solar system. We spent a lot of time looking at cosmology and talking about galaxies and dark energy and dark matter and sort of things that are way out there. And I mean way out there, even for an astronomer, they're way out there in some sense, right? I know dark matter is around us. It's a local thing, but we usually talk it when we talk about the grand scheme of the universe, right? The global, if you like, or the universal view of our universe itself. So this podcast, we're going to concentrate more on things that are within our own solar system.
We're bringing it home.
This kind of fits to the podcast we had last time. So if you didn't get a chance to see episode number 18, please look at that.
Please do.
And by the way, if you like this podcast at some point, please give us a thumb up. And if you haven't subscribed yet, please think about subscribing to our channel. That way you keep informed of when these podcasts happen.
Every week we bring you content, just about.
And just a heads up, for those who view this on a regular basis, that starting with the fall semester, so that would be late August, we may have to change the date and time of the podcast.
Right.
Just because this is, we're doing this during our normal work hours, if you like.
Right.
And we thank the University of North Dakota and the College of Arts and Sciences and the Department of Physics and Astrophysics that allow us to do this podcast.
Absolutely.
But our schedule changes semester to semester, so we may have to do other things during this time period. So we'll keep everybody informed way ahead of time if things need to change.
Right. We'll probably know something around middle August.
Yeah. By then, our schedule.
And we'll start advertising the new schedule.
That's right. And also, I also like to make a point that anything that Robert and I say on this podcast are our personal opinions and not necessarily the opinions of the university, the college, the department, the state of North Dakota, the United States of America, North America, the world, the solar system, or the universe as a whole.
Yeah, we don't want to.
That's a lawyer's type of disclaimer.
Yeah,
we
cover
everything.
And we don't want to annoy any of our alien listeners in a few hundred years.
So last podcast we talked about the sun.
The sun. Yep.
So in this podcast we're kind of going to continue that discussion, but we're with other things in our solar system.
Right.
And in this case we're going to try something new. We usually show individual slides, but now we're going to try to use a PowerPoint presentation. So hopefully this will work. Keep our fingers crossed.
All right. So shall I bring up the first?
You shall.
All right. So here we go.
Okay. So hopefully everybody is seeing this and hearing us.
Hopefully. If you can't hear us.
Please let us know in the chat.
Definitely.
So Robert, what do you think this first image is? It looks very much like something that's close to home.
It looked very like the moon. So I got to admit, my first guess was the moon, and you corrected me. And as soon as you did, I realized it was 100% correct. This is Mercury.
This is the planet Mercury. This is the closest planet to the sun. Of all the planets that maybe you'd like to go on, this is probably one of them that you'd have to be very careful where you go.
Yes.
In the sense that if you were on the sunlit portion of Mercury, because it's so close to the sun, temperatures are hundreds and hundreds of Fahrenheit. It's way above what we have here in North Dakota this summertime. So if you don't like the temperature outside...
It might be about the temperature of Texas, though. I hear they're really having problems right now.
You never,
Yeah.
Now, the interesting thing about Mercury is that it looks, as Robert mentioned, very much like the surface of the moon and the fact that it's heavily cratered. Now, there is no appreciable atmosphere on Mercury. A lot of times, like the moon, we'd say the moon has no atmosphere at all. But when we look very carefully, there is outgassing that occurs on things like the moon, including Mercury. They have like a sodium atmosphere.
Right.
So atoms are coming off the surface. A lot of that's due to the bombardment of the sun rays on the surface of these objects, and that emits atoms, essentially. And these atoms then can gain high enough energies that they reach escape velocity, so they're driven off the surface of these objects. So that, if you want to be really technical, you would say that is an atmosphere. But it's not a traditional atmosphere.
It's not a traditional,
as we think about here on the Earth, for example.
It's not elements that are traditionally gases.
Now, a lot of times when we're looking for evidence of atmospheres, what we look at, especially if we're having, let's say, a space probe that just flies by close to the surface of these objects, is we look on the edge. So in this image at the top, you can see the edge of Mercury. And what we look for is some signs of a limb haze.
A haze.
And that's how we can see a tenuous type of atmosphere if it's not so obvious, right? It's something that's more subtle. Here you don't see any limb haze at all. Right. So, the atmosphere that it may have is very temporary, very tenuous, but it's not something that, if it was made of pure oxygen, it would be something that you could live and survive and breathe because it was just so low density. It's not breathable in that sense, at least to us. So it looks very much like the surface of the moon being heavily cratered. Now, the interesting thing about Mercury is it's very hot then on the sunlit side, but on the far side of Mercury, away from the sun, in the nighttime, if you like, it's extremely cold. There's no atmosphere that allows that temperature to circulate around from the daylight side of the heating to the back side, in the nighttime part of Mercury to kind of equilibrate a little bit to balance out the temperature. If you don't have that insulating blanket as an atmosphere, then you're going to have these wide extremes of temperatures from the day side to the night side.
Right. And I got to admit, I do have to wonder about that a little bit, because the rock surface would heat up on the daylight side, and radiational cooling is very inefficient. So the rocks would actually probably still be incredibly hot for a very long time on the dark side.
Right. So you can think of that, and that's interesting statement, because we use that here on Earth, and that gives rise to the greenhouse effect.
Yeah.
So we know, for example, that the surface of the Earth radiates, and the positive, more energy comes off the night side of the Earth in the form of infrared radiation. And that's from the solar heating of the surface during the daytime.
Right.
But we have an atmosphere, clearly, and that atmosphere acts like that blocking or that shield or a blanket. So it allows the infrared, then some of that electromagnetic radiation to reflect back down to the surface. Mm-hmm. In this case, the heat, the infrared heat on the night side of Mercury just gets radiated out into space, causing the cooling effect.
Right. So it would be cooler. I'm not disagreeing there.
Right.
It's just, I think the rocks would hold on to that heat for a very long time.
And we have measured the infrared coming off. You know, you can measure that coming off the night side of planets, especially objects that don't have an atmosphere. Yeah, so that's clearly the case here. This image is kind of neat. When you first look at it, you almost think of, what are those little small scale structures that you see here, almost like dirt piles.
Like that?
But if you actually look really closely at the those objects, they actually turn out to be little tiny craters, craterlets, if you like, right? And so it's kind of your eye playing a little bit of trick. You're always looking for a three-dimensional type of structure to see here, when actually it's all stuff that's all craters rather than things that are positive relief, being hills or mountains. This is a negative relief, if you like, being like craters or valleys.
Right. And this is from the Messenger mission, if I'm not mistaken.
Yes.
So you know, it's actually fairly close to the surface here because there's no atmosphere to get in the way. So this is pretty good resolution, where, you know, we're used to looking at the moon and seeing features that are tens of kilometers wide. This is probably getting on the order of a little less than a kilometer.
Right. In fact, I want to make a statement that essentially all of these images that we're going to show here in this PowerPoint presentation are images courtesy of NASA.
Oh, right. Yes.
Okay, so we have to make sure that we credit the right people on this. So this is, yes, taken from the Messenger spacecraft, which went in orbit around Mercury, our first time ever. And we had Mariner spacecraft that flew by Mercury, but they never went in orbit around Mercury.
Right.
So Messenger provided us with our best views of the surface of Mercury.
Another neat little factoid about Mercury I'll point out is of the terrestrial, the rocky planets, Earth and Mercury are the only ones with intrinsic magnetic fields.
Interesting. Yeah. You know, in the point of view of observing, there's certain times of the year where Mercury is far enough away from the sun that you can actually see it with your eye. It's bright enough that you can see it with your eye. You don't need binoculars or telescope. You just need to know where to look and when. And this usually occurs shortly after sunset and also shortly before sunrise.
Right.
So sometimes in the news, and certainly on the internet, you can look up when is the best time to view Mercury.
And you'll need a clear horizon.
Right.
You will need no trees on your horizon.
That's right.
It's not like it gets very high in the sky.
And I've seen Mercury, you know, many times, of course, because knowing when and where to look.
Oh, I'm jealous.
And here from North Dakota, it's really easy to see because we have that flat, clear horizon, no hills in the way, no mountains in the way, no forest in the way.
I'm going to have to go out and try then.
Yeah.
I've never managed to see it.
Oh, yes. I've seen it many times since I've lived here since 2007. So we're in a prime location to see planet Mercury.
Nice.
Yeah.
Excellent. Okay.
So let's move on. So this is a view of actually the surface of, Robert?
Oh, this was Venus. I recognize those features.
Now, this is not something that you would see with your eye alone. This is actually radar imaging.
Mm-hmm.
Now, one of the things we know about Venus, and Venus is actually one of those planets that are very, very easy to see with the unaided eye. So it usually occurs, you know, depending on the time of the year. After sunset, you'll see it as a very bright object, usually in the west, or sometimes before sunrise, you'll see it as a very bright object in the east. And one of the things about Venus, it's very, very bright, and it's very white in color.
Yep.
And when you look at it with a telescope or with a pair of binoculars, it's the white that shows up, and that's reflection of sunlight off of the clouds on Venus. So Venus is completely cloud covered.
Right.
So if we lived on a planet like Venus, and I mean like not in the terms of its temperature, but the amount of cloud cover, we would be highly disappointed.
Well, we would have
Because
never seen
we've
stars.
never seen the stars.
Right.
And so that would be, and would astronomy have advanced to where it is today? Probably not. We would have had to wait for the invention of rocket technology that would allow us to get above the atmosphere of our home planet so that we could finally see what's out there.
Yep.
And all of a sudden, all of this stuff would become, visible. All the stars, the Milky Way galaxy, other galaxies. And it would be fascinating what type of paradigm shift in your understanding of things beyond your home planet would occur once you get above that cloud cover.
Right.
So if there are any Venusians on the surface of Venus, they may be surprised that we actually exist here on the Earth if they never had a chance to see it.
I will go so far as to say, would they have invented rockets in the first place with nothing to look at?
Yeah, well, nothing to motivate them.
Right.
Unless there had, I'm going to take a negative side of civilization, unless you're warring with your neighbors and you want to build missiles, and that technology would naturally evolve during peace times to scientific exploration of what's away from
kind of like what happened with us.
Kind of like what happened with us. The liquid fueled rockets were developed in the 30s with Robert Goddard. He flew the first liquid fueled rocket. But, we always also tag on the advancement of rocketry with von Braun, and that obviously is the V2 rockets, the V1 and the V2 rockets during the Second World War. So that the military purpose really drove the advancement of rocket technology. And I mean modern rocket technology. I don't mean fireworks or solid propellant rockets that were invented, first by the Chinese, many years ago. I'm talking about, advanced rocket, more modernized form of rocketry. Mm-hmm. It was definitely the war that advanced that.
Yeah, I would argue even in the Orient, the rocketry was advanced as a thing for war.
Yes. Well, solid rockets were used by the British in the Revolutionary War. Or in the War of 1812, think of the U.S. national anthem, right?
Rockets red glare.
Yeah, exactly. That was the British firing in. There was all solid propellant rockets.
Yep.
So they were used as a weapon, for many years, obviously.
Absolutely.
But Venus itself, because of that cloud cover, that infrared light has a hard time escaping the surface in the nighttime off the surface of Venus even, and that bounces back down and heating up the air. And so the atmosphere of Venus is actually has very dense, very high pressure, tens of times the pressure here on the Earth. And the temperature is hot. We're talking, like 500 degrees Celsius, if I remember right.
Right.
You could cook a 16-inch pepperoni pizza in a couple minutes just by laying it on the surface of Venus.
It'll melt lead.
You don't need an oven.
Right.
To cook your food. So because we can't penetrate down through the cloud cover unless we landed on the surface or got extremely close, the most efficient, cost-effective way, if we have an orbiter, a spacecraft in orbit around the planet, is to actually use radar to probe its surface. Mm-hmm. And that's the images you're seeing here. It was taken from the Magellan mission in the 1990s, also another NASA mission, to survey the surface of Venus by pinging radar off its surface. Right. And what we discovered is there's a huge number of volcanoes on the surface of Venus. In fact, we think that some of these volcanoes are actually active today.
Ooh,
so it's a highly volcanic active surface. We've seen changes in the surface. So people have looked at volcanoes and then compared them to radar images taken by spaced out over a year or two, and seen the structure change. We know that there's volcanic activity, present day volcanic activity on the surface of Venus.
That's neat. I was not aware of that.
Yeah.
Cool.
So that's pretty interesting. So the surface of Venus is not at all like the surface of the Earth in that sense.
And these features, by the way, that I'm showing with the cursor, are actually euphemistically called pancakes.
Right.
Because of their flat circular feature. They are volcanic in nature, and they are actually they're lifted up. They're above, kind of the opposite of the Mercury picture. These are actually rising up out of the surface instead of going down into it.
Right, and the magma floods that whole area, so it doesn't give them a large height, right? They get these flattened like cone, cinder cone-like structure to them.
Yep.
So Venus, and by the way, a major constituent of the atmosphere of Venus is sulfuric acid.
Sulfuric acid, right.
That's not a place I want to be without a spacesuit.
I don't even know that I want to be there with a spacesuit.
The temperature will kill you, the high pressure will kill you, and the actual makeup of the atmosphere will kill you.
Yeah.
So in the future, when we explore the surface, when humanity steps foot for the first time on the surface of Venus, we're going to have a lot of protection in order to do so.
Well, I know some guys that are working on trying to figure out a way to make a lander last on Venus for more than a few minutes. So we're working on just how to get our machines to keep working there.
Well, the Soviet Union landed a couple landers on Venus. The United States or the Europeans have never done this before. And those landers, I think the maximum time they lasted was on the order of 70-some minutes. That's because the pressure and the heat gets to them. Eventually, electronics fail.
Right.
So there is this, natural evolution of electronics here for different extreme environments to get them to work. And one of them is the high heat that we would experience on the surface of Venus.
Yep. So they're looking at cooling it to get a little extra life, but then also insulating it to do that. Right. So next one.
Yeah, so this is a beautiful image. I love this.
Yeah,
this shows like sort of a valley-like structure. This is on the surface of Mars, taken with the NASA Curiosity rover. You can see part of the rover in the frame of the image here in the lower right, and also you can see some of the tracks on the surface of Mars. And this is nice because what it almost shows is you can imagine yourself just walking through this valley and making footprints as you go along. For the first time ever, nobody has walked on this surface of this planet, but you can imagine, you can see yourself just doing that.
Right.
Now, unlike Venus, the surface of Mars is relatively cool on the average temperature and has very low pressure. So it's not like you can walk out there like you could today with a shirt and shorts on and sandals or something like that.
Considering it's warmest, it gets up to the temperatures of summer in Antarctica.
Well, no, we have extreme temperatures like 20-some degrees Celsius on Mars.
We have? Okay.
Don't forget the peak times, right? On average, it's extremely cold. Yeah. But the pressure is just so low. How low is the pressure? Well, you could take a pan of water, and if you set it on the surface of Mars, it would explosively evaporate because of the low pressure.
Right.
So obviously we wouldn't be able to live in that environment. We'd need a spacesuit. But yeah, this is a real cool image. Now this shows, of course, the sun is below the horizon. You can kind of see some of the glare, the scatter of the light to the upper left in the image itself. But it's just beautiful. I mean, it almost looks like, almost Earth-like in terms of a desert environment.
Right. Almost.
Almost.
I see a lot of features that you won't find in any Earth desert.
I mean, it's not surprising that humanity, next body that they're going to explore is going to be Mars.
Absolutely.
I mean, we've already been to the moon, but the next one will be Mars. Yep. Just because the amount of design that we need is not a lot compared to trying to step on the surface of Venus.
Right.
So
or
Mars,
Mercury. Or...
Right. I mean, and of course, other planets like Jupiter and Saturn, Uranus and Neptune, they don't have a solid surface to step on in that sense, right? They're the gas giants, if you like, of our solar system. But yeah, you can just visualize yourself walking through here, strolling along and exploring.
Yep. Looks good to me.
Now, Robert, is this our moon? If not, is this Mercury or is this something else?
I recognized it wasn't the moon.
It's not, definitely not our moon.
It doesn't really look like Mercury either because the craters are pretty shallow.
Right.
So I'm going to sit there and say this is a moon of something, but actually we had a discussion beforehand.
So this is the what? The largest?
This is the largest asteroid in the belt. This is Ceres.
And where does that belt lie in our solar system?
Between Mars and Jupiter.
Now, did you hear the joke that involves the asteroid belt?
No.
I recently heard that the universe is expanding. It's soon time to loosen the old asteroid belt.
Wow.
Moving on. So yeah, this is an image taken of the largest asteroid in our solar system.
Okay, Ceres.
And that was taken by the Dawn spacecraft, also a NASA spacecraft. Now, if you look very carefully, sort of near the center, a little bit to the bottom center, and then off to the right a little bit, you'll see that there's some white patches. Maybe, the mouse pointer,
right there.
Robert will point that out. So we got that one location and a location over there. When that was first spotted, as the Dawn spacecraft was approaching Ceres, people were wondering...
so right here.
Yeah, right there, and there's a little bit off around there. Yeah. So people are wondering, what is that white deposit? Is it somehow ice?
Right.
Because you naturally think of the Earth,
Right.
right? I mean, there's ice on the surface of Mars even that we see, you know.
Yep.
Carbon dioxide, frozen carbon dioxide. In fact, we have the polar caps on Mars that come and go, right?
Right.
Depending on the seasons at the time on where you are on the poles of Mars itself. So people naturally thought this, but it turns out it's not that at all. It's actually salt deposits.
That's just nifty.
And it is cool. It's almost as if the impact that caused these craters, and these two in particular, drove some of that salt deposits under the ground up onto the surface. And that has a higher albedo, which is a measurement of the fraction of light that gets reflected off the surface of a body. It has a higher albedo than the surrounding area that doesn't contain those salt deposits.
Right. Now, okay, well, we'll move on. I've got another question there, but.
Yeah, keep going.
Okay. My question is this, because I've had it posed to me. How does ice survive on a body like this? Because it's a vacuum and ice sublimates. And in fact, the lower the air pressure, the gas pressure, the faster it sublimates. So how could water ice survive in a place like this? Well, the answer, partially at least, is that it is cold. The ice we think of is in reasonable set of temperatures. It's ice 5, I believe it's called. Or ice 3, that's right. There are other types of ice. And when you get out to these distances from the sun, the temperature is low enough that it's driven into these other forms of ice, which do not sublimate because they become as hard as granite.
Right, so here's an example of that to illustrate this point. Go into your freezer, get out an ice cube. Okay, now don't swallow it, so don't choke on it. Put an ice cube in your mouth and clamp down on it with your teeth. Take it out and look at it. Did you make an impression of your teeth in that ice cube? And the answer is going to be
yes,
because it's relatively soft. Right. But if you took a piece of ice from the surface of an object like this, at these extreme cold temperatures of hundreds of degrees below zero, and you did that same experiment, you're not going to leave any impressions in that piece of ice. It's like putting a granite rock in your mouth and
trying to
put a bite mark in it.
Right. So this is part of why ice can exist on bodies this far away from the sun and farther, is because the ice is not the ice you're thinking of from your deep freeze or your freezer. This is ice that we do not experience here on Earth at all, except in a lab. So
exactly.
Here we go with the next one.
Now, Robert, do you know what this planet is?
I actually knew what planet it was. This was Jupiter.
This is Jupiter.
Absolutely.
Now, the reason why I selected this image, by the way, this is taken from the Juno spacecraft, which is in orbit around Jupiter right now, another NASA mission. It's your tax dollars at work here, exploring our solar system.
Trying to figure things out.
The reason I picked this is because you can see there's a green light sort of near the middle, a green spot. Now, we'll get Robert to point that out to you with the
right there.
mouse. Now, what do you think that is, Robert?
I didn't know at first. I had to ask you that. I would have never have guessed, but that is a lightning strike.
That is a lightning strike. So not only does the Earth have lightning storms on it, but other planets like Jupiter and others also have lightning. Saturn is another example.
So why is it green? Do you know that one?
So the green then is due to the atmosphere, the composition of the atmosphere. Okay. Remember that in the lightning, what you're having is an electrical discharge. And so that lightning is passing through not a vacuum, but passing through the atmosphere. The atoms that make up that atmosphere, think of it a column of air, for example, are being energized because of the high energy that's passing through that column of air. And so that causes the electrons to be stripped off of those atoms. And those electrons then recombine. They create emission lines. So you get this emission of light. And of course, the color that we see with our eyes, is dependent on the type of atoms that it's in that gas. And that gives rise to the various colors.
So with that color green, I'm going to say this is probably some oxygen that was ionized.
So we have oxygen, we have nitrogen, right? Okay. We have the normal hydrogen, the primordial stuff, and helium. But you have this mixture. Yeah, so that's where the color is coming from. Just like the northern lights. Why do you have the different colors?
Right.
Of the, you have green dominates as the nitrogen.
Is the nitrogen.
Right, and then you have red for the oxygen.
Right.
And you have these other colors where you have different mixtures, of different types of atoms that make up the composition of our atmosphere.
Yep. I mean, it's neat stuff when you start finding out what causes these colors. But Dean and I have discussed some of this, that you get a green color from ionizing oxygen.
Right. Think of comets.
Right.
Comets are mostly green a lot of the times because of this same kind of.
And because of the nitrogen again.
Yeah.
Because nitrogen gives off a nice green color.
That's right.
So.
And Jupiter, by the way, that's our largest planet in the solar system.
Right.
The second largest planet in our solar system, I think everybody would recognize, is the one that you see here. Woohoo. And that is the planet
Saturn.
Saturn. Now, Saturn, of course, was observed for the first time in a telescope by none other than
Huygens?
Galileo.
Oh, Galileo. That's right. There. He drew ears on it.
Yeah.
He didn't know.
So Galileo made the description. He didn't realize there was a ring system, set of rings going around Saturn. He said they looked like teacup handles.
Right.
And it's much easier, of course, to see the rings when they're on one side of the planet or the other side of the planet rather than looking at them projected on the front of the planet. So he knew there was something weird about Saturn, but he didn't quite piece that together, that it was the rings. But you mentioned...
Yeah. He thought it was ears on the side.
But who did you mention when you first...
Huygens.
Right, so Huygens did a lot of...
Okay. Huygens is the one who just did a lot of observations and first realized they were rings.
Yeah,
right?
he did that detailed study of the ring system of Saturn for his time.
Okay.
With a telescope. So he gets...
I'm going to mention, this is from the Cassini spacecraft that orbited for Saturn for many, many years, over a decade, I think.
Right, and then they finally cut the money from the program and dumped the probe into the atmosphere of Saturn.
And people were crying over that.
Yes.
I know several people who are involved with this mission. So
yeah, I mean, I'm a great believer in if a mission is running, we should keep it going if it's supplying useful data. Once it doesn't supply useful data anymore, then that's time to get rid of it.
Then plow it into the atmosphere.
Well, and I think one of the arguments from NASA was there's only so much money to go around, so how are we going to develop new projects if we keep spending it on supporting old projects? And the other argument was, in this case, is we want to make sure that we control the spacecraft by causing it to enter the atmosphere of Saturn rather than maybe dumping on a moon and contaminating the surface for later future exploration. So there was some worry about that.
Yep.
So this is the typical sort of planet that we see. The realization, early on, we thought that Saturn was the only planet, and this is before the Voyager spacecraft, explored Jupiter and Saturn, Uranus, and eventually Neptune. And we thought that Saturn was the only planet that had a system of rings. But today we know that Jupiter has a system of rings.
Right.
Saturn, of course, but the planets Uranus and Neptune also have rings. So actually half of the 8 planets in our solar system have a ring system.
Yes.
So rings are not sort of, rare. They're actually, there's a lot of them out there, right? So it's a common thing. And we also know of dwarf planets, objects that orbit beyond the orbit of Pluto. One of them in particular has a ring system.
Yep.
So we're seeing it in other environments as well. So actually, rings are more common than we once thought.
Indeed.
Which is kind of cool when you think about it.
Kind of cool.
Now, Robert, what is this planet? This is really strange. What the heck is this?
This is still Saturn. Saturn. Was one of those, holy cow, how is that happening moments where we were looking at, I can't remember which pole it was of Saturn.
This is the North Pole, I believe.
North Pole.
Yeah.
And bottom line, this is a storm, kind of like the Great Red Spot on Jupiter, except it forms this nice hexagon.
Yeah, that's a 6-sided structure that you see there. But interior to that, you see all kinds of circulation. So you're looking down at the pole of Saturn, and you can see really something that people really didn't see before Cassini had a good view of the polar regions of Saturn.
Right.
Voyager flew by close to the equator of Saturn and never flew over the pole to allow us to see these kind of views that we're seeing here.
Right. And you can see storms embedded within the storm. And it's a neat little thing. And we're still working out all the dynamics and details of how that hexagon formed. So again, as I've said on many shows, come join us. There's plenty to figure out. There's plenty of new things to explore and find out about our own solar system, much less the universe as a whole.
Yeah, if you want a great example of what we call in physics hydrodynamics,
Look at this.
And complex systems that involve hydrodynamics, all you have to do is look at the atmosphere of, example, Saturn and figure out all this type of interactions, a very, very highly complex system.
Absolutely.
Lots of turbulence involved as well. And one of the things about turbulence is, Do we understand turbulence in nitty-gritty detail, Robert?
Absolutely not.
Absolutely not. It's one of those unsolved sort of mysteries in physics.
We can numerically detail it for very brief periods of time, but eventually any turbulent system goes outside of the boundaries of what we know. It's going to do new things. You've got to reset your boundary conditions and solve the equations.
Right. So turbulence is one of these things that we're really studying even today to try to figure out the nitty-gritty details and what happens over very long timescales.
Right. So here we go.
Now, this is also an image taken from the Saturnian system. What do you think this is an image of, Robert?
Oh, this is the rings. I remember
This is the ring
image.
system. Now, the reason why I picked this image, this is also from the Cassini mission, is because if you look and sort of in the middle, you can see gray. You want to use the mouse to illustrate this. You're looking at the shadows cast by the particles that are part of the ring system. So the sun is the upper part, the upper right, and the sun is coming down towards the lower right, lower left, creating these shadows that you see here from the ring particles. It's amazing. Yeah. So you get almost a 3D perspective of what the different heights of these particles are like relative to each other.
Right.
You can see they vary in sizes, as you can see. They're almost like a picket fence type of feature that you're seeing here, but the pickets are of different lengths.
So it's like these are probably sand grain sized. All these out here are probably sand grain sized particles, whereas these have some icebergs.
Well, some big as houses and even larger. Right. These are huge, like,
and they're
structures.
casting shadows back onto the smaller particle stuff.
That's right. So in the future, you can imagine we'll be sending robots that would fly up to these icebergs, and explore them in detail. Now, you can't walk across. It's not a solid surface.
Oh, definitely not.
If you could zoom in on what was happening here, there's individual particles that are in their own independent orbits going around the planet Saturn.
Yep.
But to be able to fly a spacecraft in amongst those particles and study them in detail, that is for the future, and that would be amazing.
That would be amazing.
So there's a lot, we're trying to illustrate the point here. There's a lot of undiscovered territory in our solar system. So it may, we've talked in the past about what it would take to go to the nearest star to our sun, one that's over 4 light years away. With present technology, you're talking about, tens of thousands of years to get there. So why go now? Let's wait for technology to develop in the future that maybe we can come up to some significant percent of the speed of light, maybe 5, 10%. Yep. And therefore, instead of taking 4 years, maybe it would take 400 years to get there. Right. But that's a lot better than 50,000 years with sort of present technology, 50,000 to 70,000 years. But and you might say, oh no, I'm so disappointed. It's not going to happen in my lifetime. It's not going to happen in my child's lifetime or his child or his child. It could be, thousands of years before we get to that point to explore other stars. But it's okay. Why? Because there's so much to explore in our own solar system.
Right.
There is a lot to look at.
I'm disappointed I'm not going to be around for several missions that are launching now.
Well, there's talk right now on the board of exploring the planet Uranus.
Yes.
And by the time that spacecraft, it was agreed to do the funding and to build the thing and get it out there, we're talking about really in the 2040s.
Right.
You're talking about, at least 20 years before that spacecraft is in this Uranian system like that to explore. I mean, that's getting up there. So people who are building these spacecraft now, you may not be alive at the time they're actually sending back science. But there's so much to explore in our solar system. We have plenty of things to look at for the next 1,000 years.
Absolutely. So, moving along, this is still in the Saturnian system. This one, I remember the image coming out from Voyager spacecraft. No, not Voyager, Hubble. One of them.
Robert, I remember this. I first saw this, I think, in 1977.
Right.
When, as a young person, I went with my parents to watch the movie
Star Wars.
Star Wars. Isn't this the Death Star, Robert?
It is not. It is not. But yes, we've got our first images back of this particular moon of Saturn. Its name is Mimas. And originally, it looked like the Death Star. You could see a little bit of surface texturing and that big giant crater in the middle with a little bump coming out.
You want to show that with the mouse pointer? Yep, so it's clearly obvious it's on the right-hand side there.
So here's that nice crater.
With the central peak.
With a central peak in it. And so you couldn't see any details, so there was all this texturing down
Right.
here.
So the Voyager image in the late 70s was a very low resolution
Very
image
low
compared to
resolution.
this one.
Yeah. So now we know that it's just that this moon took another hit from another object that was almost big enough to break it.
Well, you can look at the diameter of that crater and compare it to the diameter of the moon itself. That's a significant fraction of the moon's diameter. And people have done calculation of the amount of energy that it took to scalp out this crater, the impacting body, how much mass would have kinetic energy of impact. Yeah. That if it would have been a little bit greater, it actually would have split this moon in two, or multiple pieces.
Right.
So it almost got destroyed, this moon.
Absolutely. And it's great. So where is the object that's hit it?
Well, that's it. Interesting. Is it buried inside of this?
Right. And so again,
and some of those particles go into making the moons in Saturn. Now, Saturn recently, they found several more moons. These are small objects, though,
right,
orbiting Saturn. And Saturn now has the most moons of any planet in our solar system. It finally surpassed Jupiter once again.
So what we're asking is were fragments of this impact blown off and became moons of Saturn, or were they crushed even finer and just drifted into the ring system?
Well, when you talk about the ring system, because you're talking about individual particles, aren't they really small moonlets?
The argument could be made.
So one would wonder, because of the ring system is so much greater than that around Jupiter, that you'd always have more things orbiting Saturn than you would Jupiter. So Saturn would always be the king of having the most number of moons in our solar system.
That's just neat. So moving along, this is another Saturn moon. I recognize this one immediately because this is one of my favorite moons.
Now, when I first look at this, Robert, it looks like there's like rockets going off at different places on the surface of this object. What's going on here, Robert?
These are geysers. These are water. In fact, we now know they are water and ice geysers.
Now, how do we know that?
Because, again, Cassini got to take some spectroscopy. And so we know it's water and we know it's ice particles. And I think Cassini even flew through them.
Bingo! Cassini actually flew through the plume of these geysers.
Right.
Imagine that. That's what you call making in situ observations.
Absolutely. And in fact, it found salt. So it's not just water, it's salty water.
And there's plans on the board that people want to send another spacecraft to just go to this moon to study these geysers.
So the name of this moon, by the way, is Enceladus.
Enceladus.
It's also got one of the highest albedos of any object in the solar system. It reflects like 90% of the light that falls on it. There is so much just neat stuff about this moon.
In fact, we think there might be a liquid body of water under its surface.
Yeah.
Under the frozen surface of Enceladus.
And so people ask, well, with it so cold out there, how can you generate enough heat? Well, its orbit around Saturn is very eccentric. And when you add in that it's got another large moon called Titan that's out there, the gravitational differential, the tidal force that is exerted on this moon makes it flex, like sitting there bending a paperclip rapidly. And when you feel it, you can feel it warm in the middle of that paperclip.
Exactly.
So that's where the heat to melt this water is coming from. Is this moon is literally being squeezed and expanded and squeezed and expanded. And it's generating heat.
Yeah, you could take like a rubber ball, right? Measure its temperature, and then squeeze and let it go, squeeze and let go, squeeze and let it go several times, and then measure its temperature again, and it'll be warmer.
It'll be warmer. And that's what's going on with this moon.
Except it's gravity doing it, not a human being, of course, or some life form squeezing it.
Great stuff.
So this is cool. So this is like a prime location to explore further in the future. Mm-hmm. In fact, there are plans we're starting to get together to do just that, which is really, really neat.
It's neat. It's great stuff.
Okay, looking at the next planet from our sun beyond Saturn is the planet
Uranus.
And this is an image of Uranus taken by...
I'm going to guess that's James Webb.
That's James Webb Space
Telescope. That's some
Telescope.
bright imaging.
Now, one of the things you'll see is clearly there's a planet. You can see the blue color and some white surface feature on these outer atmosphere.
Things I noticed.
But you see the ring system.
You can see the rings around it.
There's the rings of Uranus.
And then you got all these hot spots, which tell me you've got upwellings, so that's storms.
Now, it was interesting. Back in 1986, Voyager 2 did the close flyby of the planet Uranus. Mm-hmm. Now, during that time, when that occurred, the images of the surface of Uranus were all blue in color. It was bland.
It was bland.
To an atmospheric scientist, it was boring.
Mm-hmm.
There was no spots to be seen, not like you see on the planet Jupiter or on the planet Saturn. And so the atmospheric scientists were extremely disappointed in the view of Uranus. In fact, in some sense, that almost killed any chance of going back to Uranus in the near future.
What's
the point? Now, people, and we'll see this in a second here, people looked at the moon system, they looked at the ring system to kind of look at, interesting features and things, but the planet itself was boring. But what we discovered, because we can look at Uranus from the Earth, from our telescope, whether it's the Hubble Space Telescope, now of course you see this image with the James Webb Space Telescope, or even with the Keck telescopes on the ground in Hawaii, that we discovered that Uranus is not always bland, that there are times when we see atmospheric features, we see spots, we see stripes and so on. And it turns out, as far as we would think what's going on, is that there are times when the surface of Uranus in the optical, we're talking about here, look bland and boring, but there are times when there's more activity. It's a seasonal variational type things.
Right.
Now, Uranus is really neat. And the neat thing is, it's actually tipped over.
Yes.
Almost 90 degrees.
Mm-hmm.
So when you fly by Uranus, like we did in the Voyager 2 days, the planets are like spread out like on a bullseye pattern. And you fly by the system almost at the same time, all at once.
Right.
Where when you fly by Jupiter and you fly by Saturn, the moons of the planets were lined up in the equatorial plane roughly. So you pass one, then you pass by another one, and another one gives you time to explore them one at a time type of thing. But this system is completely different. It's tipped over on its side. So the pole of Uranus then is pointed towards the sun rather than its equator in that sense, if you think of the rotation. And so the question we have is, what tipped it over roughly 90 degrees? It's almost as if it was hit by a large, massive object early in the formation of our solar system, and somehow that tipped it over.
In fact, that's pretty much the only way it could have done it.
Well, that's the only way you can think of, right?
Because that would have taken just an enormous amount of energy.
Exactly. And that stuff, you can't look at the surface of Uranus like you could the surface of the moon and say, well, here's a location of a huge impact that occurred, because it's a gas giant. All of the debris of the body that collided with Uranus would be buried down inside of the planet itself. And who knows, some of the debris may have been kicked up or caused to form the ring system, maybe some of the moons of Uranus. In fact, we know that some of the moons look extremely bizarre, and here is one of them.
I don't know the name of this one.
Miranda.
Miranda, okay.
Okay, so this is an image taken also by the Voyager 2 spacecraft. And when you look at this moon of Miranda, one of the things that's striking is this, it looks like it's a jigsaw puzzle that's been put together.
Notch out of it?
Yeah, there's like pieces that don't belong. They're not the same structure as nearby regions. It's almost like you've got chunks of chocolate that's been melted inside of some object, and you see these different sort of things, right? These different geological features. It's almost as if the moon was broken apart at one point, and then it reassembled together, maybe by its own gravity, and you have what we have today, then billions of years later.
Frankenmoon.
There you go.
But you know what the geologist part of me notices? How many craters do you see?
Yes, that's right. So it's not heavily cratered.
It's not heavily cratered, which means it's young.
Yes, exactly. But how young is it? I mean, that's the thing. And also, I mean, these separate pieces, were they separate and craters were created on those separate pieces, then the whole thing came together? So even if you look at the most heavily cratered regions of this, that maybe not telling you the actual date of the assembly.
Right. It might be telling you when that piece was assembled.
Yes, exactly. When it was heavily cratered, but not necessarily when this whole system was put together.
But yeah, its surface is fairly young.
So this is one of these objects we need to study in detail.
Yes.
This is a geological heaven, a gold mine, right? That we need to get there. We need to land on the surface of this object and explore the various regions. So there's a lot to uncover. In fact, there is talk now by groups of scientists of putting together a mission to go to Uranus and to go into orbit, not just fly by like we did with Voyager 2, but actually to go into orbit and study this system in detail, including its moons like Miranda, like you see here. Like I talked about already, it's still on the drawing board. It hasn't been improved by NASA. It's actually one of the higher ranked approvals in this decadal survey of looking at the solar system exploration. So it's up near the top. I think it's even the top one, if I'm not mistaken,
I don't
at
know
the
that.
recent
Yeah.
decadal survey. And so there's a lot of serious thought going into putting together an orbital type of mission. But
Nice.
like I said, even if they start funding it today, by the time it gets there, you're talking about the late 2030s.
Right.
And so unfortunately, it's going to be a few years before we get some dramatic new scientific results
They
coming from this
sigh.
system.
All right. Shall we move? All right.
The next planet from the sun, in fact, the most distant planet from the sun, because
Yes.
they've taken away that designation from poor Pluto,
Poor Pluto.
is the planet
Neptune.
Neptune. So Neptune, the only spacecraft that we had that flew by Neptune, this was by the Voyager 2 spacecraft in 1989. And unlike Uranus, which the spacecraft flew by 3 years prior, Neptune is not boring. You can see the features on this in the atmosphere of Neptune. So that's the image that's on the furthest left here. You can see it has a great dark spot.
Nice.
And then to try to make a
Nice
connection
big dark
with the
spot.
great red spot on the surface of Jupiter, for example. You can see some smaller clouds, some
clouds.
white clouds. There are some clouds that go by pretty fast called scooter clouds, if I'm not mistaken. So there is different structure to the atmosphere. If you're an atmospheric scientist, all of a sudden there's lots of stuff that you can study then in the planet with the planet Neptune.
Yep.
Okay. Now the middle image that you see here is the one taken from the Hubble Space Telescope, so 2021. And the one on the far right is a recent image taken with the James Webb Space Telescope. Now you could ask, why is the Hubble Space Telescope in the middle so different than one on the far right? You want to explain why they look so different, Rob?
One of the biggest things is the far right one, the Webb, is in the infrared. So it's looking at the heat. And whereas the Hubble spacecraft is designed to look at visible light. So they're looking at two different regions of the electromagnetic spectrum is one of the things. And we can't see infrared. So number two is this is a color altered, a color enhanced version. And they choose color palettes to do these images so that they make certain features pop and snap so that we can see them better. And so the James Webb is showing us that there's regions of comparatively really hot material coming in on Neptune.
And that's through those atmospheric spots.
Right.
So they're releasing a lot of infrared light. And the other thing is the dust particles that make up the ring
Rings.
glow brightly at infrared wavelengths. And that it's easy to see that than in the infrared. And that's also a feature that stands out with the James Webb Space Telescope.
So there we go.
Now, what used to be the ninth planet, but is now a dwarf planet,
Yep.
due to the change in the designation by the United Nations of Astronomy, also known as the IAU, or the International Astronomical Union. Okay, that's the United Nations of Astronomy, as I like to say. These are images taken of the flyby from the New Horizons spacecraft that flew by Pluto. They gave us our first real good view of the surface of Pluto and its moon system back in 2015.
Right.
And so these images have been pieced together. The background thing that you see, like stars and the Milky Way, whatever it's supposed to be, that's fake, of course.
That's fake.
in that movie. But the actual image that you're seeing of the surface, that's real data. So that's a view of the surface of Pluto then as the spacecraft was flying by at the time. And you have this kind of neat way of viewing it, this representation using this little movie. You can visualize yourself flying over the surface of Pluto and what it would look like.
Yeah.
Now, there's
cool.
a lot. Now, one of the things that we tried to do is send a spacecraft to Pluto early on. Pluto's in this highly elliptical orbit where it actually gets closer to Neptune, right, to the sun. And other times it's much further away, beyond Neptune's orbit. Right. So there are times when it's the closest to the sun, and then when it's furthest from the sun. When it's closest from the sun, what we observed was a lot of outgassing that was occurring on the surface of Pluto and actually build up an atmosphere. So it's like a temporary atmosphere, so we thought, right? That was the prevailing wisdom before we flew by. And as the planet moved away from the sun in its orbit, eventually becomes so cold that those gases then fall back on the surface, if you like, and the atmosphere goes away.
Right.
So then when Pluto gets closest to the sun again, then the gases evaporate out, make this nice atmosphere, and then that atmosphere freezes out, if you like, and it settles down on the surface again. Now, it takes roughly, 249 years to go around the sun once.
Right.
So if you're waiting for a time when Pluto's closest to the sun and want to do some measurement of its atmosphere, and then you say, I'm going to skip this time, I'll wait for the next time. Well, you're going to have to wait about 250 years. So it's not going to be you doing those measurements, right? It's obviously going to be future generations.
Speak for yourself.
So Pluto came close to the sun, the closest to the sun couple decades ago, and there was this push by planetary scientists to get a spacecraft out there as quick as possible to observe that atmosphere. Now, that was delayed until 2015, but still, even though we got out there a little late, there was still some residual atmosphere. It had not all frozen down on its surface. And of course, we've seen this wonderful topography and the other features of Pluto, its moon Charon, and its other moons that it has in this Pluto system itself.
It's a complicated system.
And the final image we're going to show you is of what's the surface of this?
This is a comet.
This is a comet. You could almost visualize it standing somewhere in the desert area of California or somewhere.
Yep.
It's just amazing. This is actually an image taken by the Rosetta spacecraft, right, when it was flying by a comet. And it actually had a probe that landed on the surface of the comet, and the Rosetta went into orbit around the comet itself.
Yep.
But you can it's such a cool image. You can visualize yourself walking on the surface of this comet.
And the different colors are basically different materials.
Now, the thing you have to be careful with a comet, of course, has so little mass, gravity's very weak, so it'd be easy to escape the surface. If you were strong enough with your legs, you could jump off the surface of the comet, and depending on the comet's mass, you might reach escape velocity. You could move away from the comet.
It's not even a matter of you go into orbit around it, you just drift away from it.
You just drift away. So you better have another means of coming back, like a jetpack, or maybe you're tethered to something or whatever.
Yep.
And so it's going to be very tricky to explore the surface of comets, in person in the future.
The movie Armageddon got it very wrong.
Exactly.
So.
Okay, Robert,
That's it.
That was our grand tour, if you like, of the
there.
solar system.
And so now we're back.
And so, since we're at the end of our time, one of the things we mentioned is the fact that if you're interested in science, or if you're not interested in science, maybe you're interested in arts, all of that stuff goes hand in hand. Please consider coming to the University of North Dakota. We have wonderful programs, both for on-campus type programs, so you're here in person, or if you can't do that, we have lots of wonderful programs and courses that you can take online. So you could be anywhere you want on the earth and beyond. As long as you have a way of connecting in with the internet system, then you can access these courses.
Yep. It's great stuff. You should come see. And right now is, usually a good time to come, but, pay us a visit. Come
Exactly.
see us.
We have wonderful seasons here in North Dakota.
We got all 4 of them usually. So.
Now, the next podcast will be next Tuesday. That's June the 27th, starting at 3 p.m. Central Daylight Time. And we always leave you with a quote. So today's quote is actually from, do you remember?
I don't remember.
Socrates.
Oh, Socrates.
Right.
Socrates.
Yeah. So the quote is, and it's a very fitting quote given the subject nature of today's podcast, the quote is, "Man must rise above the earth to the top of the atmosphere and beyond, for only thus will he fully understand the world in which he lives." Thank you for watching.
Thank you for watching. Y'all have a great week.